So this idea is using the symmetry of the shape to our advantage. So we know, remember, if it's an even function, we've got symmetry in the y-axis. So function negative x is function x. If I want to integrate from minus a to a, I can take advantage of the symmetry and go twice from 0 to a. And I guess the main reason we do that is because, well, 0 is usually a fairly easy number to substitute in. But if you had a horizontal shift, now, okay, I'll concede this is a rare instance, you might never see it, but think about it. If you did have this situation where you notice, hang on, we've shifted this even function to c, and then you're integrating an even amount around that c, then surely the same rule's got to apply, that the integral from c minus a to c plus a would be twice from c to c plus a. Because all you're doing is you're saying, okay, I've got this even function and I've shifted along. How useful is that? As I say, I don't know. But just keep those sorts of things in mind if you spot them. Odd functions, and perhaps this one might be even more useful. Function negative x is negative function x. So that's the one where we integrate from minus a to a. We can save ourselves a lot of time because we can say, oh, well, that's 0. And you don't actually have to do any integrating at all. So with that one, if you notice a horizontal shift. So same idea. If we've shifted across to c, and we're integrating from c minus a to c plus a, again, we can say, well, hang on, it's going to be 0 because we've got that rotational symmetry about the point of c on the x-axis. So again, the same idea. And I say, rare, but you never know. It could come in handy. This one certainly comes in handy. The integral from 0 to a of function x is the same as the integral from 0 to a of function a minus x. And again, that has to do with, well, you've shifted, but you've also reflected because of the minus x, and you end up with the same area. But it's easy enough to prove, and I'll do it via substitution. So we want to find the integral from 0 to a of function a minus x. So if I let u equal a minus x, the u becomes minus the x. So when x is equal to 0, u is a, and when x is a, u is 0. Substitute that in, we get minus the integral from a to 0 of function u, but then I can swap the limits and make it positive, and because it's a definite integral, well, it doesn't matter what pronumeral I use, because we're going to substitute in anyway, and so there it is going to be the same as function x dx. Keep this in mind too when you're looking at symmetry. Remember, if it's the same type of function multiplied together, you'll end up with an even function. If they're different types of functions, so one's odd, one's even, you'll have an odd function overall. So again, if you notice that, you might save yourself some time. So let's do some examples. So sine cubed. Now that we've seen all the techniques for the trig integrals, the temptation is to, oh well, I'll go and integrate sine cubed. But remember, sine is an odd function. So when you cube it, you're saying odd times odd times odd. Well, odd times odd would be even, but then even times odd brings it back to being an odd function. So I don't have to do any work here. I can say, oh, okay, I know that's equal to 0. And I'd probably, justify it by saying, oh, well, that's an odd function or something like that. Now, here's the one where that idea about the a minus x comes in handy. Because to expand that out is going to be a bit difficult because of the square root of 1 minus x. So, okay, I've got to come up with a substitution. But if I notice the 0 to 1, I can go, well, I'm going to change that. I'm going to replace x with 1 minus x. And what happens then is I just have the square root of x. And that's very easy to expand out compared to the first one. So we get x to the half minus 2x to the 3 on 2 plus x to the 5 on 2. Add 1 to the power over the power. Sub in 1, sub in 0. And we've got our answer. Again, we've saved ourselves a lot of time. All right, it's a pretty specific situation. It's got to be going from 0 to some number. But you can always substitute in that number minus x for x, and it might make the calculation easier. Now, improper integrals. So an improper one is one where we've got a boundary which is actually an asymptote or something like that. So in that situation, well, we can't actually evaluate at the asymptote, so we investigate the limits, what's happening as it's getting closer and closer. And there may or may not be a solution. So if we have a look at our hyperbola, and if I want to integrate from 0 to 1, now our hyperbola is going up to infinity. I can't sub in 0. But the question is it still possible to find the the answer to this. So we integrate it like normal, but instead of having 0 there, I'll just put n or some pronumeral. And then we'll say, okay, I'm going to investigate as the limit of that pronumeral approaches 0. And then we just integrate as normal. Well, dx on x is log x. Substitute in 1, substitute in n, I get minus the log of n. So we think, well, all right, what happens to that as n approaches 0? Well, the log of 0 is undefined. So in this case, no, that integral can't be calculated. That doesn't have an answer. As opposed to this one, xe to the minus x squared, and we're going from 1 to infinity this time. So we're going off to infinity. So again, I'll replace the infinity, that's what's causing me the problem, with some pronumeral. And I'll say, well, we want to investigate the limit as n approaches infinity. And if we integrate xe to the minus x squared, I get minus half e to the minus x squared. Substitute in the n, substitute in the 1. Now, e to the minus n squared. So it's our exponential, but our backwards one. So as n is approaching infinity, I know that that exponential is approaching 0. So I can come up with an answer for this one. So the e to the minus n squared would be 0. So I'm just left with the minus e to the minus 1, but times the minus a half out the front, and I get 1 on 2e. So it's one of those interesting things where you would think you've got an infinite area because that's just keeping on going and going, but you actually come up with a finite answer. It's similar to, I guess, in series and sequences, where we ended up with a limiting sum. Even though we had an infinite number of terms, we could come up with a finite answer. So it's the same sort of idea. We've talked about this, but it's worth mentioning again. If you can trap the integral between two areas, then a lot of our problems, you will have noticed, involve that idea to working out what the integral is. So here's one from the 2009 paper. Again, you'll notice it's question 8b. So the last question. They gave us the graph of our hyperbola, y equals 1 on x. So n's an integer greater than 1. And the area under the curve, and they're going from n minus 1 to n as the rectangle they've drawn in. So show that 1 minus 1 on n to the power of n is in between these two values. Okay, so we're going to use that idea. The area of the inner rectangle will be less than the integral, will be less than the area of the outer rectangle. So the inner rectangle, well, it's got a width of 1, a height of, well, the curve was 1 on x, so it'll be 1 on n. And the right-hand side, the outer rectangle, the height was 1 on n minus 1. And our integral will be in between those two. So we have log x going from n minus 1 to n is in between 1 on n and 1 on n minus 1. So subbing into my log, I get the log of n on n minus 1. Right, but if you look at what we're trying to prove, there's no mention of log in there. But there is e to the power of, which is the inverse of logs. So, before I exponentialize, again, if there is such a word, I've multiplied by n, because you'll notice in the inequality we're trying to prove, it was n on n minus 1 to the power of n. This will allow me to get that in as the power, because I can use my log law to now bring n in as the power. So I get 1 is less than the log of n on n minus 1 to the power of n, which is less than n on n minus 1. Now I'll exponentialize, which we can do. The inequalities will be maintained because the exponential curve is continually increasing, just like the log curve was. So that's not a problem. So we get e is less than n on n minus 1 to the power of n. Was that what we had to prove? How far have I got to go? There must be another step, is there? Oh, turn both sides upside down. Okay, because they had actually n minus 1 on n. But remember, with inequalities, if you turn it upside down, you change the inequality sign. That looks horrible like that, of course. So I'll rewrite it that way, with the inequalities the correct way. And also, I made use of negative indices because that's what they asked me to show. So I made it match what they wanted me to show. Okay, so Old Cambridge, which I've copied and it is in the handout. But notice they use 2a minus x instead of a minus x for some reason, but it's still the same idea. Don't know why they use 2a, to be honest. 4i's in our textbook, and then there's the tradition that every Extension 2 student must go through.